All right, well, I will begin with a word of prayer. As soon as I find a blue marker. Oh, there it is. All right. All right, so here we go. Heavenly Father, we thank you for this day. Thank you for the rain and for this time we have to study your creation together. Help us to understand more about it and encourage the students if they're struggling, Lord, in this course. Lord, in your name I pray. Amen? All right, so I asked you guys the question, are these two functions inverses of one another? How do we decide?
No.
No? No is not going to be worth much without explanation. So we should calculate f of g of x. Right? What do we get then? So I suggested you could think of this as like f of g, right? And you can just plug g in the place of x. So what's that give you? That gives you g cubed plus 2, right? But what is g? G is the cube root of x minus 2, right? So we've got the cube root of x minus 2 cubed plus 2, right? What is the cube root of x minus 2 cubed? Well, that's x minus 2 again, isn't it? So that's x minus 2 plus 2, which is x. Ooh. Let's strike one against the answer no. Now, it's not enough that f composed with g of x is x again. Like, that's part of what we need for g to be the inverse of x, f. But we need also the g composed with f of x. So if we look at g composed with f of x, does that also give us x? So I could think of that as g of f. Plug f. So I've got the cube root of, what do I got? Cube root of f minus 2. But what is f equal to? F of x is equal to x cubed plus 2, right? That's a cube root, right? So cube root of x cubed plus 2 minus 2, which then is what? Oh, that's the cube root of x cubed, which is, by the way, x again. So yes, in fact, g is equal to f inverse, because it satisfies the two needed conditions to be the inverse, right? F composed of the g of x is x, and g composed of f of x is x. Now, technically speaking, the x I put in one side or the other should be different. This one's kind of quirky in the sense that the domain of f and g are the whole real line, and the range is the whole real line. So we don't need to really make a conceptual distinction between the x that goes in this side and the x that goes in that side. All right? How would this example turn out if instead of using a third root, we used like a square root? How would this go? What if I tried to do, f of x equals to, say, x squared plus, we could do 3 this time, and g of x equal to the square root of x minus 3. Would those be inverses of one another? What do you guys think? No? Why not, though? Because I'm asking the question? I mean, that's one way to look at it, I suppose. Let's work it out. So what is f composed of g of x here? F of g of x is, let's see here, allegedly f of, I can think of it as f of g. Plug the g formula into the f, we get what? G squared plus 3, right? So I get the square root of x minus 3 squared plus 3. What's the square root of x minus 3 squared? Yeah, it's x minus 3 again. And so, well, that's looks like it might work, right? We do need to try the other one, because we need both for it to be the inverse. So that's g of f, so to speak. And that means I plug the f formula into the g. I've got the square root of g minus 3, excuse me, f minus 3. which is to say the square root of, what was f of x? X squared plus 3. So we've got the square root of x squared, which is what? What is the square root of x squared?
Something I. It's I.
That's sometimes true. When is it true?
It's a negative x.
Like, for example, is the square root of minus 5 squared equals to minus 5? It's not, right? Because the square root of minus 5 squared is the square root of 25, right? And so that's 5, which of course is not equal to minus 5, yeah? So what is the square root of x squared? In fact, generically speaking, the 2nth root of x to the 2n is actually absolute value of x. Because it's plus or minus x, depending on whether x is positive or negative. So the answer here is not x, it's actually absolute value of x. Which means that f is not the inverse of g.
No, because you got rid of the 3.
I mean, these are not inverse functions of one another. So f and g are not inverses. Because we need x, we don't need absolute value of x, all right? In fact, what did we say was the needed condition to find an inverse for a function? Remember, it had to be what, 1 to 1. Is f of x a 1-to-1 function? Yes. No, it is not, though. So what does the graph of f of x look like? X squared plus 3, right? That's a parabola. Opens up from the y-intercept of 3. Is that 1-to-1? Most certainly not, because that fails the horizontal line test, right? And it's exactly this plus or minus business that's coming up here, isn't it? See, because we have, for x, we have this corresponding minus x, which are both giving you the same output. This is not a 1-to-1 function, so no, it cannot be inverted.
So no matter what, if you did the 1.
The problem, as stated, they're not inverses. There is a way to make them inverses. How do you fix that? Same. I mean, what's the trouble here is the horizontal line test is giving you two things, right?
Yeah.
So to make the horizontal line test work out, one way you could do is just to take the domain of f and get rid of half of it. So like example 4, if we had, f of x equals to x cubed plus 3 for, the domain of f equal to 0 to infinity, like that. So just define the domain of f to only include positive x, right? Then you've only got, the graph is only half of a parabola, and it's only half of a parabola, and so you don't fail the horizontal line test, And then you can let g of x be what it was, and by the same algebra, we can, by the algebra we just did, right? We have the same algebra, we get f of g of x equal to x by this algebra right here, right? And we have g of f of x is equal to the absolute value of x by this algebra right here, right? But what's the difference? We only look at x in the domain of x, f rather. So this x is assumed to be in the domain of f, but we're assuming the domain of f is non-negative numbers, so the absolute value of x is just equal to x in that case. And there you go, now they're inverses. So sometimes we can fix functions not being inverse of one another simply by chopping down the domain of one or the other of them. All right? This process of chopping down the domain is called restriction. This will be important in your pre-calculus class if you go on and take that class when you talk about trigonometric functions, especially their inverse functions. The concept of restriction is important there. I don't have too much more to say about it here, though. So does this make sense in terms of, remember we said last time the range of the function is the domain of the inverse function. The range, the domain of the function is the range of the inverse function. Like it's vice versa, right? So for my example 4, what's the range of f? So the range of f, we can just look at the graph, right? Because like the picture for example 4, you just make this part dotted, right? Example 4, I've just chopped off the left half of the parabola, right? So like the graph of f is this guy. All right? And the graph of g is what? The graph of g is this one down here. So the range of f is all the y values. It's 3 to infinity. And what's the domain of f inverse? It's also 3 to infinity. Right? And I may put g there because I'll put g because my point is that g is equal to f inverse. The domain of f, on the other hand, by assumption was 0 to infinity. Right? What's the range of g? See the range of g? It's 0 to infinity. So all of this together is evidence that f and g are inverse functions. Okay? So last time I talked to you guys about what's the definition of inverse function, what's one-to-one function, and then how do we calculate the formula for an inverse function, right? Today I'm starting with the question of somebody gives you a formula, how do you check if it's the inverse or not, right? You have to compose f composed with g and g composed with f and see if they both work out to x. All right? By the way, there's an asymmetry here, right? Because it is true that the 2nth root of x to 2n is the absolute value of x, but what you might also want to know is that if we take the 2nth root of x to the 2n power, that is equal to x. Like the other direction, you don't get the plus minus. It just like that.
Okay. Is that something we should put on our note sheet?
That is something you should know from previous algebra.
Oh.
Yeah. Now, but many people don't, and that's okay. If it's okay as long as we notice that we don't know it and make adjustments, right? Yeah. So on the other hand, the odd root, the 2n plus 1th root of x to the 2n plus 1, so this would be like a 3rd root or a 5th root or whatever. This is just straight up equal to x again. And it's, if we have the 2n plus 1th root of x raised to the 2n plus 1, we just get x again. So odd roots are very forgiving with the algebra. The absolute value thing doesn't happen for the odd roots. It's just the even roots we got to watch out for. They're the ones that are kind of conniving. And the reason for that, if we understand it graphically now, is that when we look at y equals x to the 2n plus 1, what's it look like? Generically speaking, y equals x to the 2n plus 1 kind of looks like this, It's a one-to-one function, so it's got an inverse function, and that inverse function is the 2n plus 1th root. So like the inverse function of x to the 2n plus 1 is literally the x to the 2n plus 1th root. And these equations here reflect the fact that composition of the 2n plus 1th power and of an odd root and an odd power, they're inverse functions. Whereas these equations right up here reflect the fact that the even power function and the even root function are not inverses of one another, unless we make the additional restriction that x is positive. And that's not surprising because when we think about the graph here of x to the 2n, what's it look like? It looks like this, right? So of course, it fails the one-to-one, it fails the horizontal line test, right? So of course it's not injective, therefore it can't have an inverse. Right? If that absolute value wasn't there, then that would mean that the 2nth root and the 2nth power function are inverses of one another, but they're not. Again, unless we do like example 4 and restrict. So, okay, enough of this. Let's find some more inverses, yeah? How about let's see here. What if I asked you guys? Now I'm gonna make this example up. I'm not sure. We'll see. We're gonna try to do it. If it doesn't work, well, we'll see. Okay. We're gonna try it though. Let f of x equal to 3x over, let's say x squared minus 1. I'm going to back up a second here. Get rid of that square, make that a 2 instead. There we go. Find the inverse function. Find the formula for f inverse of x. So how do we do this? What's our step number 1? Remember I told you? Number 1, we're going to write y equals to 3x over 2x minus 1, right? Thanks. And then I need to do what? Solve for x, right? How do you solve for x? Multiply 2x minus 1 on both sides. Okay, we got that. Multiply it out, right? 2xy minus y equal to 3x. You want to isolate your x's, right? So put all the stuff with x on one side. So I've got myself a 2xy minus 3x equals to y. Factor, what's that?
You did it right.
Oh, okay. I did it right. That is a good sign. Because I did something really wrong with my son today when we were doing math before I got here. Yeah.
You guys are doing discrete math?
No, I'm teaching him calculus at the moment. I'm trying to teach him calculus. Old enough?
He was a little boy.
No, not that son. No. I have 4 sons.
Oh.
So, but his main goal, like I number the pages of our notes, right? 1, 2, 3, 4. We're up to like page 80. His main goal is to cover up the page so that I can't write down the next number before I forget the number. Like this is his whole goal. And so if he'll immediately tear the page away from me after I'm done writing on it, so I don't know the number for the next one if I haven't. Yeah. And also if I like get up and go to the bathroom or something while I'm gone, he'll like change the number on the top of the page so that I think it's 80, but it's actually like, it's like 80. Let's take an 84 and change it to an 89. He likes to do this a lot. Yeah. I think he's really focused more on that than the calculus, so it's not really going that well at the moment. What's that?
How old is your son?
I think 14, but I think he's 14, yeah. So.
Is it because like with our exam with the numbers and stuff, is that should be 3 and then 34?
Calc is actually easier.
It's okay. Just like one of those.
So, well, yeah, I mean, I'm teaching him calculus, but it's really algebra. I keep teaching him algebra steps, right? Because no one really learns algebra in algebra.
Is he in middle school?
It's true.
They teach calculus in middle school?
We're homeschool. So now that we have x all on one side, we factor x out. And we got 2y minus 3 equal to y. Like that. Yeah?
Yeah.
Now we solve for x. So divide by 2y minus 3, we get x equals to y over 2y minus 3.
And that's your x value?
And that right there is your f inverse of y. If you want to write the formula in terms of y, there it is. But what did I ask for? I asked for the formula in terms of x, so we got one more step. So this right here was my step 3, right? And then my step 4 from last time was to swap x to y if you need to. So Step 4, f inverse of x is equal to x over 2x minus 3. Okay? You guys can do this, right? Yeah? Now here's a follow-up question. What's the domain? What's the range? So the domain we can figure out from what? We need what? We need 2x. We need 2x minus 1 not equal 0, right? So if you think about that, that means the domain of f is going to be like minus infinity to, so we need what? We need 2x not equal to 1. In other words, we can't have x equal to a half, right? So we need minus infinity to a half, union with 1/2 to infinity. There's your domain. Everything except for a half.
So you don't need to have, you don't get that from here, you get it from the original.
Yeah, I got that from the original, exactly, from the original right here.
Okay. So you can get the domain and the range before you do it. It just depends on which.
Well, how would we figure out the range for a function before? What do we do? We graphed it, right? But there's a trick we could use here now, right? We just found the inverse function exists. Yeah, we're here it is. There's the inverse function, right?
Okay.
And we also know what's the relation between the range and the domain. Remember, the range of the function is the domain of the inverse function, right? But we can figure out the domain of the inverse function without graphing, right? We can figure out the domain of the inverse function just from looking at the formula. What do we need for the domain? So right here, look at this one, right? This is the formula. We need 2x minus 3 not equal to 0 if we look at the star equation, right, from the formula.
Yes.
Which is to say what? Yeah.
I have a question. Why you have the x equals y over 2y minus 3, and then you have f to negative 1y?
Mhm.
Why do you have that written there?
Because once we solve for x, we can recognize this is the stuff in y, and we set the stuff in y equal to the inverse function of f. I mean, whatever you solve it for x, that whatever's left there, that is the inverse function written in terms of y. And then I flipped the y to x to get the formula.
Is the domain of the inverse function, is it negative infinity, so 3 over 2 union 3 over 2 to infinity?
Yes. Very good. Santa used her brain.
Yeah.
It's very good. Merry Christmas to us all. Let's see here. Ho, ho, ho. Let's see here. I need to watch that sequel to A Christmas Story. Where was I? Now, we could have figured out the range before by graphing, right?
Yes.
Yes. There's about a
50%.
40-60 chance that's going to go right in here from what I've seen on the test. So graphing is perilous, right? But looking at a formula and seeing where it's not defined, that we can all do without too much danger. Now this makes sense that 3/2 isn't in the range, because if you look at the original formula, the leading coefficients are 3 over 2, right? So the horizontal asymptote to the original graph would have been 3/2, right? So this is not surprising that 3/2 is missing from the range, but it's nice that we didn't have to draw a picture, isn't it? Yeah. Okay, that's example 5. See if I can find you a more exciting example.
That was so exciting.
I know, but I want an even more exciting example. So. Now there's a theorem that I should tell you guys, and that we must learn and understand, all right? And this is, you know, important theorem. Here it is, theorem. If A comma B is an element of the graph of f, then b comma a is an element of the graph of the inverse function. What this means is that you can graph the inverse by taking the function and just taking, points in the function and flipping the x and y, and that's how we can graph the inverse. So like, example, and do you guys know, this just means element of, if you're wondering, that's just, element means element of. That's just fancy math speak for element of. And now that I've expanded the abbreviation, I've undone the whole purpose of writing it. So I hope you're happy. Example 6. So shorthands, if you have to always explain the shorthands, it becomes not a shorthand. Hey, but I feel your pain, because I was just complaining to my wife. Like, I teach this course online, and like the online people, they speak in this like
Text language?
this cacophony of abbreviations. It's like SRV phase 2. It's like, what? What are you talking about? Like, oh, check the roster. Okay, I can check a roster, but I don't know what SRV phase 1 is. SRV phase 2, so it's student roster verification phase 1. That's just an example. It is just ubiquitous over there. Anyway, so I feel your pain. I mean, I know this is the same thing to you, right? But there's actually a difference, which is that this is universal and standard mathematical notation that if you pay attention, mathematicians will slip into if they don't pay attention, because it's what we write in. But anyway,
You have your own alphabet?
do we have our own alphabet?
Yeah.
I mean, some people do, I guess. I don't personally have my own alphabet, but I mean, I've never really found the need. But so here's an example. If we had a graph like this, all right? And so let's suppose that we've got 0, 1 on it. And up here, maybe we've got 3, 5 maybe. And maybe over here, we're looking at like, maybe minus 8. Oh man, why did I make that 1? Well, I made it 1 already, so it is what it is. This is going to be like a third. All right? So you got these 3 points. This is a graph. Y equals f of x. All right. This is given. So you're given the graph of f of x. Is this a one-to-one function?
Yes.
I think it is, right? It passes the horizontal line test, right?
Yeah.
So it's one-to-one, which means we can find an inverse for it. Let's graph the inverse as best as we can with what's given, right? So we just have these 3 points. So all we can do is flip the points. So like instead of minus 8 1/3, I get 1/3 minus 8. So that point flips to here. 0, 1, that's easier. That flips to 1, 0. And 3, 5 flips to 5, 3, right? And so there you go, up to the limits of my artistry. There's a graph of y equals f inverse of x. You're given the purple graph. You can create the red graph using the theorem.
Oh, so it doesn't matter that the 18 stays negative, because all the other ones you're just flipping the numbers. So
Yeah, well, I just flip the numbers here too.
okay.
It's always just flipping the numbers. Look, and there's something we can say about this. What's the symmetry here? Right? The symmetry, the way it's described is this. If you look at the line, y equals x, right? What's going on here is we're reflecting the graph of y across the line y equals x, right? There's an equal, if I did it exactly right, there should be an equal distance, say from this point and that point, right?
Yeah.
This distance and this distance should be equal if I did the graph right.
Okay.
So we can also find the graph of an inverse function using this theorem, and also the principle that we reflect the graph across the line y equals x. But I would encourage you, I mean, if you can see the flipping the graph across the line y equals x in your mind's eye, if you're really good at that, great. I struggle with that at various points. So I try to fall back on the map, follow the points. Following the points is much safer. Yeah? And if you look at the example I erased earlier, if you look back in your notes at the one with the example 4, if you look at the red and the blue graph there, you'll see it's exactly the same. We took the parabola, half the parabola, and you flip it over across the line y equals x, you got the square root of x minus 3 graph. That was an example of this earlier, right? Example 7. Let me erase the element of there. That was supposed to be a line. Okay. Excuse me. I guess that might be like y equals to, I don't know, x plus 1. What's the inverse function? Can you graph the inverse function? Suppose that's f of x, right? It passed the horizontal line test? Sure. Definitely 1-to-1, right? We can find its inverse. So there's this theorem, like corollary to the theorem. Do you know what corollary is to a theorem?
It's similar to the theorem.
Similar to the theorem? I think it comes from like the word flower. It's kind of like something that's flowered from the theorem, you know? And so the one is that if you have, let me just say it in words, x-intercepts, x-intercept goes to y-intercept, and vice versa, right? And horizontal asymptote goes to vertical asymptote. In terms of the function versus its inverse function, it means that there's this dual relationship. If you have a vertical asymptote in your function, you're going to get a corresponding horizontal asymptote in the inverse function. If we go back and we graph example 5, we'd see that play out. But that was supposed, let me try to draw that. I can't draw a line with anything up here. Good grief, it's all curvy and everything. It's kind of more like a line. There we go. Okay, so my point to you is just this. It's helpful to use that as a principle to graph. So like here we have 0, 1 is my y-intercept, right? For the inverse function, I get an x-intercept of 1, 0. Right? And I just need one other point. So, what other point do you want to fix? Do you want to pick on the line to flip over? Say 2, 3? Is that a point on the line? I think you're right. Up here, right? 2, 3? How do you know that? I plug 2 in, I get 2 plus 1 is 3, right? Great. Now the inverse function, what point do we have on the graph of the inverse function? If 2, 3 is a point on the function, 3, 2 is a point on the inverse graph on the inverse function, right? So, so roughly speaking here, right? Now I know, by the way, I also know just from the geometry here that like the reflection of a line across a line is going to be a line again. So I know that 2 points on the graph of the inverse is enough. That fixes it, right? And if I had something to draw a line with, oh, I do. Aha! I almost forgot. Ooh.
That's such a smart idea.
I think this is what it's for. It's the only thing I can figure. COVID? What's a joke? What's COVID? See here, there you go.
You're so smart.
So, oh, that didn't go well.
Oh, that's great.
Okay, try it again. You try it again.
Oh, man.
Do it again. You can do it. I'll hold it for you.
No, I did the wrong point. Come on, guys. Look, this is the point on the line. This is the point on the given function. I'm supposed to connect these two dots.
Well, I see. I'll hold it. I got you, sir.
That's okay. It's okay. I'm going to freehand it. Oh no. They never intersect. No, it's bad.
They're supposed to intersect.
Oh, wait a minute. Do they? Oh, yeah, it does. They shouldn't intersect, should they?
If you go to a place to buy coffee, you come up with something green.
Thank you.
Crazy, right? I was saying the same thing. Disgusting.
Hey, don't be fake. Don't have macho, okay?
That is disgusting. You go to a coffee place.
No, this is mixed. It should be parallel. Think about it, right?
Yeah.
Because the line y equals x is parallel to the given y equals x plus 1. So if you reflect it across that, it just gives you this other, the red line down here, the parallel line. Listen, let's take a second here. Let's work out the formula for it. Y equals to x plus 1, right? Solve for x. It's easier here. X equals to 1 minus y. Wait a minute, is that right? You guys need to stop talking. I can't hear myself think. So x equals to y minus 1, right? And then that is f inverse of y, right? Which means f inverse of x is x minus 1. So, and yeah, this red line here, this would have y equals to x minus 1, right? That would be the formula for that. So it makes sense. I think for this one, I don't know. I always prefer finding the formula as opposed to the graphical method. But you got to be aware, there are problems on every next test, like I've ever given in college algebra, where I don't give you a formula. I just give you like the purple graph and ask you to graph the inverse. So all you have to do is pick enough points to get the sense of what it looks like, and flip the coordinates over and graph those, and that's how you graph the inverse. It's just that. All right. So next time we begin our discussion of logarithms and exponentials and all that. So let's begin we begin by talking to you about a little bit about that. So what is an exponential function?
Exponentially growing at the same rate when decreasing at the same rate.
So let's talk about what it's not. All right? So here, f of x equals to x to the n. This is not an exponential function. This is called a what? Non-exponential function. Funny. This is a power function. All right? The variable is in the base. All right? In contrast, if we talk about f of x equal to, say, a to the power x, this is what's called an exponential function.
So it essentially just has to have a different base.
The variable is in the exponent. That was exponent. Notice that here the exponent is fixed. Here the base is fixed. So the exponent in the first formula is n. The base in this one is a. All right. And then the question is, what are the graphs of these so we have not talked about exponential functions in here before, right? We talked a lot about power functions, even all kinds of those, right? But exponential function, that's something new. And here's basically the story. What they look like, it's just this. If we have, what example I'm on? 8. So if we, for example, take y equals 2 to the x, we could graph that. So what's, you can make a table of values if you like. If you plug in, say, -4, you get 2 to the -4, which is also known as 1/16, right? Plug in -2, you get 2 to the -2, which is known as 1/4. Plug in 0, we'll plug in -1, let's say. 2 to the -1, also known as a half, right? Plug in 0, 2 to the 0, you get 1. Plug in 1, you get 2 to the 1, which is 2. Plug in 2, you get 2 to the 2, which is 4. So if we can graph that, it gets super, super tiny if we're over to the left, and it just grows bigger and bigger exponentially, as you guys have been wanting me to say for about 5 minutes. So -4, it's a 16th, and then it's at -2, it's a quarter, and then a half, and then 1, and then at 1, it's 2, and then at 2, it's 4, and so it's something like this. This is an exponential function. All right? Is this a one-to-one function? It is, right? I mean, it's clearly a one-to-one function, right? So what's the domain of the exponential? Domain of 2 to the x, it's everything, right? What's the range? It can't ever be negative, right? 0 to infinity. Is 0 included or excluded? Do we actually? It's got to be excluded. We never quite get there, do we? So it's basically all positive numbers, right? So hey, this is an inverse. This is a function which has an inverse. The inverse of it is what we call a logarithm. So definition. F inverse, so let me call this f of x for the sake of this discussion. F inverse of x is equal to what's called log base 2 of x. This is the inverse function. Log base 2 is the inverse function. And it is the function such that 2 to the log base 2 of x is equal to x. And the log base 2 of 2 to the x is equal to x. Now, I really should put maybe I should put a y in this first equation, because that's exactly kind of the issue that I'd like to point out, which is that this is for y in 0 to infinity, whereas the second one is just for any old x. Yeah, what's the question?
How do you know it never hits 0? So it always stays at 9.
Because there's no way you can get 2 to any power equal to 0.
Oh, no, you're right.
Yeah. So that's what we're going to talk about, is the logarithm and its properties, how that works. So we're going. Thanks, guys.